The lesson today is sections 4.2 and 4.3 in your textbook, and this deals with the addition and multiplication rules for probability. In lesson 4.2, we look at where we have many problems involving finding the probability of two or more events. We've already focused on finding the probability of an event, but now we're going to be combining some. So for example, at a large political gathering, you might wish to know, for a person selected at random, the probability that the person is a female or a Republican. In this case, there are three possibilities to consider. The first person is female, the person is Republican, the person is both female and Republican. So as you notice in this case, the events of being female or Republican are not mutually exclusive. They are not mutually exclusive. The mutually exclusive events cannot occur at the same time. So as we're looking at this problem, let's see if I can get to the next slide. Okay. Two events are said to be mutually exclusive if they cannot occur at the same time, or in other words, they have no outcomes in common. And we have basically two rules to follow with mutually exclusive events. The first one, or addition rules, is when we're taking two events and it says the probability of A or B, what we're going to do is add the probabilities of A plus the probability of B. And that's if the events are mutually exclusive. However, if they are not, then our rule's a little bit different. The probability of A or B is the sum of A, probability of A, plus probability of B, minus the probability of A and B. And we only use this rule when we're talking about events that are not mutually exclusive. In other words, there are events that have some common outcomes. Let's look at an example of that. The first one is found in your text, example 415, and it deals with rolling a die. And you're asked to determine which events are mutually exclusive and which are not when a single die is rolled. So we're going to use that new little definition. Getting an odd number and getting an even number. Well, what I'd like you to notice, in rolling a die to get an odd number, you've got three possible outcomes, 1, 3, or 5. In getting an even number, your outcomes are 2, 4, 6. So none of the outcomes are shared. They have no common outcomes, so we can say, oh yes, these are mutually exclusive events because there's no common outcomes. The second example is still when you're rolling a single die and we're considering getting a 3 and getting an odd number. Well, in getting a 3, there's only one outcome, that is the 3. In getting an odd number, we have these three possible outcomes here, 1, 3, or 5. And as you look at those sets of outcomes, they share an outcome, the outcome of 3. So these are not mutually exclusive events because they share a common outcome. Determine which events are mutually exclusive when a single die is rolled, and we're looking at getting an odd number and getting a number less than 4. So if one event is getting an odd number, that's still 1, 3, or 5. Getting a number less than 4 is 1, 2, or 3. So we've got a common outcome here of 3 in those two, and also a common outcome of 1. So since we have common outcomes for those two events, we say that they are not mutually exclusive. Determine which events are mutually exclusive, still rolling a single die, getting a number greater than 4, so our outcomes are 5 or 6, and getting a number less than 4, which are 1, 2, and 3. And as you notice here, none of the outcomes are shared, so we can say, oh yes, these are mutually exclusive events because they do not share any outcomes. Now, when I consider a problem like this, we've got a corporate research and development centers for 3 local companies have the following number of employees, and that data is given. If a research employee is selected at random, Find the probability that the employee is employed by U.S. Steel or Alcoa. Okay, so we're looking at the probability of being employed by U.S. Steel or Alcoa. Now, if the events are mutually exclusive, then what we're going to do is take the two probabilities and add them together. So that's our question in this problem. Are these two events mutually exclusive? Do you have anybody who is employed by two different steel companies or two different research and development centers? No, there are not. So since there are no common outcomes, what we're going to do is take the probability of U.S. Steel, which would be 110 over 1,110, because that's the total number of employees, plus the probability that they're selected from Alcoa, which is 750 over 1,110, and that gives us a total of 860 over 1,110, and then we're going to reduce that down to 86 over 111. Okay, so since the events are mutually exclusive, all we do is add the two probabilities together. Now in this case, we're looking at a medical staff in a hospital unit which has 8 nurses and 5 physicians. 7 nurses and 3 physicians are females. And if a staff person is selected, find the probability that the subject is a nurse or a male. Okay, now notice the wording here in this problem. We're looking for the probability that the subject is a nurse or a male. So when we set up our little formula, probability of nurse or male, we need to be thinking, are these two events mutually exclusive? What that means is, do we have any shared outcomes, any common outcomes? So do we have any nurses that are males at the same time? And as we're looking at our chart here, yes, we do. So we have a shared outcome here. So since it is not mutually exclusive, we're going to use the rule of adding the probability of nurse plus the probability of male and subtracting the probability of the and statement, male and nurse. So in this problem, get my pen back, the probability that the person chosen is a nurse, that would be 8/13, because we got 8 nurses out of 13 total employees. Probability of being a male, look down this column, we have 3 males out of 13, minus the probability that the person chosen is a male and a nurse, which is that one person out of 13. And our final answer for the problem is 10/13. Now, another way of looking at this problem is when I think about the statement nurse or male back up here at the beginning, I could say, well, what are all the nurses or and male or a male, excuse me. So nurses would be this 7 and this 1, that would give us the nurses, and then males would be this 2. So if we add those 3 together, that's a total of 10 out of 13. Same probability that we have by using the rule. Now, another definition we need to add to our notes is that of independent events. 2 events, A and B, are independent if the fact that A occurs does not affect the probability of B occurring. Okay, so we're going to use these 2 formulas here in on this particular problem, and I'd like for you to write these down. The probability of A and B, now notice the wording, what we did before with the addition rules was an or statement, so we're using multiplication rules for and statements. So if the 2 events are independent, and by being independent, that means the fact that A occurs does not affect the probability of B occurring. And we'll look at an example of that in a moment. But the rule just says we're going to take those 2 probabilities and multiply them now. Now, if the events are not independent, if the events are dependent, it's worded a little bit differently. I lost my slide, sorry. Let's see if I can go back to that. And the way this is worded is dependent events. This statement is read, the probability of A and B equals the probability of A times the probability of B given A. So that means what's the probability of B given that A has occurred. And that's if the events are dependent events. So let's consider an example using these two definitions here for independent and dependent events along with the rule. This example 423 is found in your text, and what we're considering is the two events: a coin is flipped and a die is rolled. Find the probability of getting a head on the coin and a 4 on the die. Okay, that's our two events: getting a head on the coin and a 4 on the die. Notice this word and. So we're looking at the probability of head and 4. So we're going to ask ourselves, are these events independent? And yes, they are independent, because here we've got probability of head is 1/2, probability of getting a 4 on the die is 1/6. Oh, flipping the coin is not going to influence the outcome of rolling the die. So we just multiply those two together. Now, we could list the entire sample space, and when we look at the sample space and the one outcome that's being referred to here is this one, that's the 1/12, where we have a head on the coin and a 4 on the die. Okay, another problem found in your text that deals with independent events. And this one's worded a little differently. Notice here we've got a Harris poll that found 46% of Americans say they suffer great stress at least once a week. If 3 people are selected at random, find the probability that all 3 will say that they suffer great stress at least once a week. So to think about whether that's independent or not, we want to know would the probability of the second person that you ask be influenced by the probability of the first person that you ask. So like if the first person says, yes, I suffer great stress, is that going to affect the probability of the second person suffering from great stress? And it doesn't. So these are independent events, and the difference here is we've got 3 of these, because we're looking at the probability all 3 will say they suffer great stress. So what we're going to do is we're going to multiply the probability times the probability. So our final answer is 0.097. I'm going to stop here and continue on the next video with the rest of this lesson.